Okay guys, this is a video on chemical equilibrium. So it follows on from the topic that we did after rates of reaction. Two topics that people can sometimes get a little bit confused with each other. So try in your mind to differentiate between the rate of reaction and the chemical equilibrium. So let's have a look at what equilibrium actually is. Okay, so you'll have met a few equilibrium reactions previously, and they apply to reversible chemical reactions. And these are reactions in which the forward reaction and the reverse reaction are both occurring at the same time. So if we take a look at our example at the bottom, that means that hydrogen is constantly reacting with iodine, but hydrogen iodide can collide with another hydrogen iodide molecule, and that reaction can turn them back into iodine and hydrogen. So that's equilibrium where that and that goes to that, and the hydrogen iodide in turn goes back to the reactants. If you sort of maybe compare that to something like if I combusted this is methane, natural gas. Okay, when I combust natural gas, when I burn it, in other words, okay, that is not a reversible reaction. Okay, so when I get the carbon dioxide and water, they don't combine together to go back to oxygen and methane. So that is represented by this one-way arrow here, whereas we represent our dynamic equilibrium by that. Now, when I have these things reacting in, let's say, a beaker okay, and they're constantly reacting together, once I get to equilibrium, once that and that have reacted, and these and this have reacted back to that, that never ever stops. This is a thing called dynamic equilibrium. And it's not static, it's always happening. So in this beaker, these are always reacting to give that, these are always reacting to go back to hydrogen iodine. It never ever stops. And very often when I ask students, what comment could you make about the concentrations of hydrogen and iodine then, and the concentration of hydrogen iodine when we reach this position of dynamic equilibrium, where everything's moving forwards and backwards at exactly the same rate? They often say to me, the concentrations of the reactants and the concentrations of the products will be the same. Okay, they're not the same. There's no real reason why they would be the same, but they are constant. They're never changing. Okay, so if the rate of the forward reaction, so the rate of the reaction that goes in that direction, is equal to the rate of the reaction that goes in that direction, then these concentrations are what we call constant. They're not equal. There's no reason why they would be equal. So we're going to look at a little graph here, which you might be confronted with in an exam. Okay, and this shows sort of what's going on during a chemical reaction and how we reach dynamic equilibrium. We're going to ask a few questions on it. See, hopefully you can maybe pause after I ask a question, and then I'll do the answer, and hopefully you can maybe get the correct answer. Okay, so if we look at this, this is just a very simple reactance going to products, a very simple chemical reaction. We have at the start here, we are on the y-axis, we have our concentration of the reactants and the concentration of the products and how they change over time. So obviously concentration of the reactants at the start of a reaction is very high, concentration of products at the start of a reaction is 0, okay? And obviously as reactants will decrease very, very quickly at the start of a reaction because they're colliding with each other, and the products will be made in a sort of equal and opposite concentration. Okay, so they will go up very quickly to begin with, and then they'll start to slow down as the amount of product and the collisions between the product slows down. So my first question to students, and when I'm doing this, would be, at what point have we met dynamic equilibrium? And I'll maybe flick back to the previous slide. Just remind students what dynamic equilibrium is, and it's the state achieved when the forward reaction and the backwards reaction are happening at equal rates. Okay, and the common answer that I'll get here is this little intersect here where people think dynamic equilibrium has happened there. Okay, but does that show that the forward reaction and the reverse reaction are happening at equal rates? Well, no. At this point, the forward reaction is speeding up, okay, and if we go back to over here, we will see at equilibrium the reactants and the products coexist with constant concentration. So this is going back to what I said over here. If the forward and reverse reaction are equal, then the concentration of reactants and concentration of products must be constant. So if we go to this graph, we're really looking for the point at which the concentration of reactants and products are constant. Well, that is whenever they plateau out here and here. So there we go. This is the point at which that dynamic equilibrium has been reached. Now, if you're an engineer and you're running a chemical process, what do you want to do to these two lines, to the line of products and the line of the reactants? Well, what you want to do is you want to push the products line up and the reactants line down, because at the end of your chemical process, you want to have none of that left, and you want to have as much product as you can possibly produce from your reaction. And this is the whole point of studying equilibrium. You will study how we change the conditions under which chemical reactions take place in order to push this line up, so make as much product as possible, and push this line down in order therefore to make as least or have as least little reactant left over as is possible. Now, what about this distance here then, or this time here? What does that represent? Well, that is how long it has taken to actually get to dynamic equilibrium, and that is a measure of the rate of the reaction. So again, if you're an engineer, what would you want to do to this line? Well, you want to push that line as far to the left. You want to reduce the amount of time required in order to get dynamic equilibrium. Now, we've already studied rates of reaction, so this is to do with rate, so don't confuse it with this, which equilibrium, which is pushing this up and this down. So in other words, making this reaction that we had as a two-way reaction, trying to make it go in that direction there. Okay, so we're going to use some terms and phrases whenever we talk through this topic, and I'm just to sort of, whenever I'm talking about various left-hand side, right-hand side, just so you know what I'm talking about. I've spoken about it here. Right, so the position of equilibrium will vary from reaction to reaction, and it will change as I change certain conditions. Now, as far as you're concerned at GCSE, we're looking at changing temperature, we're looking at changing pressure, and we're also looking at changing concentration. Now, when examiners are feeling a little bit devious, okay, and they're talking about pressure, they may not talk specifically about pressure or directly about pressure. They may talk indirectly. Now, what might they say? Well, in terms of pressure, they may say things like reduce the volume of a container. Now, provided that container, and this is where you need to be careful, if that container contains gases, because remember, it's only going to be gases that are going to be affected by pressure. If I reduce the volume of a container and that container contains gases, well, what am I doing to the pressure? Well, if I reduce the volume, I will increase the pressure. No different than if you have, excuse my artwork, okay, if you have a syringe, okay, and you have a plunger in that syringe. If you have this syringe full of gas and you block the end of it and you push the plunger in, you're going to reduce the volume and you're going to increase the pressure on the gases in there. So just be careful of questions that talk about decreasing and increasing volume whenever it's to do with gases, because really what they're probing you on there is, do you understand how pressure affects position of equilibrium? Okay, back to the terminology then. So you'll hear me and you'll read in textbooks, etc., about to the left, to the right, and in the middle. So to the left of an equilibrium, or to the left, might say also to the left-hand side, and it'd be abbreviated by as LHS. Okay, to the left-hand side just means that we have more reactants than we have products. So the equilibrium is lying towards the left-hand side of the arrow. We're talking about the arrow. To the right means that we have more product, in this instance sulfur trioxide, than we have reactant. So we're leaning towards the right-hand side, and again, right-hand side of the arrow. And in the middle just means we have relatively similar concentrations of reactants and products. Okay, so what do we need in order for the equilibrium to be achieved, or an equilibrium to happen within a system? Well, we need the system to be closed. What that means is we've nothing being added, nothing being taken away. Now, in an industrial setting, that's pretty much not going to happen because you're always taking out product and you're always adding reactant. And in actual fact, the taking out of product and the adding of reactant is a relatively straightforward way of pushing your equilibrium to the right hand side towards your products. We have it at a constant temperature, okay, so no energy is being added or removed, and we have it at a constant pressure. Okay, well, these two things are pretty achievable at industry, and most industrial processes would, of course, act at or be carried out at fairly constant temperatures and fairly constant pressures. Okay, here comes a really important slide. So this is the slide that you will use, okay, or the principle that you will use to work out whether something is added, is causes the equilibrium, to move to the left or to move to the right. So if a reaction is at equilibrium and the reaction conditions are then changed, so the reaction conditions, I should write in here, or temperature, change in pressure, or change in concentration. That can be change in concentration of reactants or change in concentration of products, either or. So if it's at equilibrium and I change one of these conditions, the equilibrium position will shift in the direction which opposes that applied change. Now, that is called Le Chatelier's principle, after the French scientist who developed the idea. Now, sorry, I've actually got material added and removed here, which is the same as what I've written down here. Now, what does that actually mean? Well, it means that, for example, with regards adding or taking away material, the equilibrium will shift to oppose the change. So in other words, if I add some material, the equilibrium will shift to oppose or to remove the material. So let's say, for example, reactants to products again. I add reactant. The equilibrium will shift to oppose that change. It will remove reactant, in other words. So therefore, if I add reactant, the equilibrium moves to the right-hand side, and that causes reactant to be turned into product. Or in other words, removes reactant. If I was to take away a product, the equilibrium will shift to oppose that change. So the equilibrium will come to the right hand side, because if I take away a product, the equilibrium will try to produce product. Therefore, it will cause reactants to turn to products. Okay. Temperature and pressure are a little bit more difficult, okay, but what we can say is that if I increase the temperature of a reaction, the equilibrium will shift in such a way as to try and reduce the pressure. Okay, if I decrease the pressure. If I decrease the pressure, the equilibrium will shift to increase the pressure. Same for temperature. If I was to increase the temperature, the equilibrium will shift to decrease the temperature, and if I was to decrease the temperature, the equilibrium will shift to increase the temperature. Now, we'll look in more detail on the next couple of slides as to how temperature and pressure affect. Right, so let's look at this table. This is a really important table, and it covers kind of all bases with regards to changes that we can make and how that equilibrium will move. So we'll just remind ourselves up here we have reactants sitting in equilibrium. So we'll call reactant 1 reacting with reactant 2 to give us product 1 and product 2. So if I add reagent, in other words I add reactant, what does the equilibrium do? Well, if I add it, the equilibrium will try to take it away. How does it take it away? It turns it into product. So if I add reagent, it moves from the left hand side to the right hand side to remove that. If I remove reagent, so if I take that away, the equilibrium will try and make it. How does it do that? It takes product, reacts the products together, turns them back into reagent or reactant, so therefore it'll move from the right hand side back to the left hand side. If I add products, so I add lots of this, remember the equilibrium tries to oppose it, so if I add it, the equilibrium will try and remove it. How does it remove it? Turns it back into reactant. So the equilibrium will move from the right to the left. If I remove product, so if I take that away, the equilibrium will try to replace it and oppose my change. So it will try and make more product. Therefore the equilibrium moves from the left to the right, and we have less reactant in there. Okay, right, temperature then, and this is where we go back to our energetics studies. we need to know what is the energetics of that reaction. What is the endothermic or exothermic nature of that reaction? So just remind ourselves that if a delta H is positive, it's endo. And if a delta H is negative, it's exothermic. Now let's take an example. I'll go to my my board here. Okay, and we'll say A plus B sits in equilibrium with C plus D, and that has a delta H which is negative. So that means that this reaction is exothermic, or in other words, it gives out heat. So what I could sort of say, now I wouldn't put it in a chemical equation because heat's not a chemical. I can say A plus B gives me C plus D plus heat. So let's say in this one, I increase the temperature. So what does the equilibrium do? The equilibrium will try and oppose that change and would therefore try and decrease the temperature. So if this is producing heat in this instance, okay, our forward reaction is exothermic. Now, what does that tell me about the reverse reaction? Well, our delta H always gives me the information about the forward. So therefore, my reverse reaction is endothermic. So delta H here is positive. So this reaction, endothermic, takes in heat. Now let's go back to our change. We increase the temperature. The equilibrium will try to reduce the temperature by taking in heat. So the equilibrium will shift towards the endothermic side of the reaction. And in doing so, endothermic reactions take in heat. And if we take in heat, that will cause the temperature to drop. So if I have an exothermic reaction and the temperature is increased, the equilibrium will move to the left. Okay, so the equilibrium always moves when the temperature is increased to the side of the endothermic reaction. Let's change the goalposts a little bit on that just to, so let's say this time we have our delta H is positive. So in other words, this reaction is endothermic. Okay, that tells me that the reverse reaction must be exothermic. So in other words, I get plus heat. So this time let's increase the temperature again. Okay, so what position or what direction will the equilibrium move in? Well, I've increased the heat. The equilibrium will try to reduce the heat. How does it reduce the heat? Well, it has to absorb it into bonds, and it absorbs it, okay, by going towards the forward reaction. The forward reaction is endothermic, takes in heat. Therefore, this reaction, if I increase the temperature, will move towards the right-hand side. If you think about it, the left-hand side produces heat, so that would make the reaction even hotter. Right? So hopefully that is pretty clear, and we'll do a few examples on the next page over, or next couple of pages over. Okay, pressure then. First thing you need to be careful about with pressure is you read the question carefully and you make sure, if you're going to talk about pressure and equilibrium, that whatever you're looking at are actually gases, because if they're not gases, pressure isn't going to be a factor. So let's take again A plus B sits in equilibrium to 2C, let's say this time, plus 3D, and we'll make they're all gases, okay? So the rule is, if I increase the pressure, it moves in the direction which decreases the number of moles of gas. So, provided you have checked your reaction, made sure everything's gases, the next thing that you do based on this, okay, and the fact that if we increase the pressure it moves to the side which decreases the number of moles, we need to go up here and we need to look at the number of moles of gas that we have in our reaction. Now, I'll actually change one of these a little bit here. I'll make that diatomic, and I'll make that triatomic. Now, so we need to count the number of moles on the left hand side and the number of moles on the right hand side. So the moles on this side we have 2 and we have 3 there, so 5 of course. These values here that I just put in, the 2 and the 3, do not contribute to the number of moles. These are just, so in other words, what I have here is 1 mole of A2, might be chlorine or something like that, and I have 1 mole of B3, so ozone or something that's triatomic, okay? So therefore I have 2 moles of gas on the left hand side. Okay, so let's say I increase the pressure. Let's go down to a rule. If I increase the pressure, it moves in the direction which decreases the number of moles. So that would mean it goes from 5 down to 2. We've decreased the number of moles. And when you're doing this in an exam, please always quote the number of moles on the right hand side and the number of moles on the left hand side. Don't just say it goes from the side with most moles to the side with least moles. Say it goes from 5 down to 2. Okay, likewise then, let's say I decrease the pressure. We go to this rule. Decreasing pressure, it goes in the direction which increases the number of moles of gas. Okay, so this time, of course, as you would expect, it goes from 2 back up to 5. So if I increase the pressure in this one, it goes to the left hand side. If I decrease the pressure, it goes to the right hand side. And if you're working in industry, obviously this process here, you're going to want it to move to this side. So you're going to work it, or to the right hand side, so you want to go at a low pressure. So we'll take an example here. I'll just make one up and we'll sort of check what sort of conditions we would ideally want this to happen at an industrial level. So let's take good old AB sitting in equilibrium to C and D. Okay, and the examiner's told us that its delta H is positive 300 kilojoules. So just to remind you, that means it's endothermic, which means the reverse reaction is exothermic and the forward reaction is endothermic. So if you just wanted to remember that the forward reaction, because it's endothermic, will take, it's good to annotate your work, okay, take in heat, whereas the reverse reaction will be producing heat, going that way, will be giving you out heat. Okay, so let's see what would the best conditions be to run this process at. Okay, well, let's deal with pressure first. Would we run it at a high pressure or a low pressure? Well, the first thing we do is we check everything's gases, which they are, and then we split our equation down the middle, and we count moles on the left. Remember, we ignore these numbers here, so that's 2 moles to there, 4 moles to there. We go back to our rule from earlier. Okay, if we increase pressure, it goes to the side which decreases the number of moles, so decreasing it will be that way. If we decrease pressure, it goes to the side, okay, which will raise the number of moles. So therefore, in this one, we want to run it at a low pressure, because we're going to go from 2 moles, sorry, to 4 moles. Now, why might that not be such a good idea? Well, at low pressure, these things are going to be quite far apart. So my reaction rate at low pressure is also low. Now, if you have a very low reaction rate in industry, that means that you are going to require very little, or you're not going to make your product very quickly, and therefore you're not going to be able to sell it very quickly. Now, how do you get over that in industry? Well, you might use a catalyst, which we did in energetics, okay, and rates of reaction. Right. Then you might say to me, alright, well that's fine then. You want a really high rate of reaction, run it at a really high pressure. Which would be fair enough. Yeah. You'll get a very high rate of reaction. But then what happens to your equilibrium? Your equilibrium now shifts to the left hand side. Therefore, you're going to get a very low yield. So you're not going to get very much. So what industry tends to do is operate at what we call, and I'll look at this a little bit later on, compromise conditions. And compromise conditions mean that we operate at sort of a pressure that is high enough to give you a decent rate, but low enough to give you a good yield. The other problem with high pressure is high pressure requires a lot of energy. High pressure requires very expensive factory setup. Okay, so pipe work, health and safety. Okay, that's another problem with high pressure. safety. If something blows up at high pressure, it blows up rather spectacularly. So your high pressure, whilst it might be brilliant, might give you a high yield, or might give you a high rate. It might also give you a high yield in some circumstances, not in this one, but it's expensive. Your factory setup is very expensive, and you have safety considerations. So for this one, just to get yield, ignoring rate, we're looking at low pressure because we go from 2 up to 4 moles. Let's look at the temperature we would use here. So we have an endothermic reaction. Okay, so if we run this at a low temperature, okay, at a low temperature, the equilibrium will try to produce heat. The only way it can produce heat is moving this way, because this is the exothermic reaction which produces heat. If I run it at a high temperature, which is what we should run this at, the equilibrium will try and absorb or oppose that change, so remove the heat, so it will take in heat, or in other words, it will go towards the endothermic side, which is the side we want it to go. So you'll run it at a high temperature. Okay, and that will give you, and that's actually good as well from a rate perspective, because with a high temperature you also get a fast rate. The only problem with a high temperature is, again, high temperatures are expensive. So you might drop the temperature a bit if you're still getting a pretty decent rate and a pretty decent yield, but if it's just that little bit too expensive to run your process at that high temperature. Okay, what about a catalyst then? Well, if we think back to our reaction profiles, back to rates of reaction and energetics, catalysts speed up the rate, and they do that by lowering this energy barrier here, called the activation energy. So if I put my catalyst in, it will do that. But my catalyst will lower the activation energy for the reactant going to product, but also the product going back to the reactant. So therefore a catalyst has no effect on the position of equilibrium, because it speeds up this forward reaction exactly the same as it speeds up the reverse reaction. So it means you get to equilibrium a bit quicker, but it doesn't actually change the position of that equilibrium. So a catalyst has no effect whatsoever on your position of your equilibrium. Okay, so I'm going to run through a few examples here, guys, and then there are some questions in your notes which you can do. So we're looking here at these examples to work out what conditions would we use in order to get the best yield, in order to move it from the left hand side to the right hand side. So let's look first of all at pressure. Well, if we look at pressure, we have on this side, they're all gases, so that's fine, tick that box. Then we have 2 moles in total on this side, and we have 4 moles in total on this side. So if we remember back to our rule, okay, that would mean we would run it at low pressure, because we're going from 2 up to 4. Temperature then, we have a positive forward reaction, so therefore that means that the forward reaction is endothermic, and we know that endothermic reactions run at high temperatures. So we would use a high degree Celsius, a high temperature. Okay, and that will, so if I put the temperature up, the endothermic reaction takes this heat away, okay, and therefore moves it to the right hand side. So as you can see, low pressure, high temperature is your answer. Alright, so if I put the next one up, and you maybe want to pause the video, that's the next one there. You're looking for pressure and temperature. You maybe want to pause the video now. Okay, so if we look at this one, again they're all gases, so that's fine. Pressure will affect the position of equilibrium. We have on this side 2 moles, we have on this side 2 moles. So pressure doesn't matter. Any pressure at all won't affect the position of equilibrium. We would run it at a pressure which gives us a decent rate. Okay, it is again an endothermic reaction, and hopefully by now we're realizing that our endothermic reactions run at high temperatures because they will take in the heat. So therefore, pressure doesn't matter and the temperature needs to be high. Again, we would just run it at a high enough temperature to get a good rate of reaction. Again, I'll show you the next one. Okay, you might want to pause the video, do it. So if you pause the video now, Okay, so if we look at are they all gases? Okay, so sorry, I should have put that in. And now that is a gas, hydrogen chloride. We have 2 moles on that side and we have 2 moles on that side. So pressure is the same as the previous one, doesn't matter. We have an exothermic reaction this time, which means on this side we give out heat. Okay, so going back that way, it will take in heat towards the endothermic side. So therefore we will run this one at a low temperature. Okay, go towards the endothermic side. Alright, final one. I think it's the final one, yeah. Okay, so again you can pause the video. So this time we have 5 moles of gas, they're all gases, so that's fine, and we have 2 moles of gas on this side, so we're going 5 down to 2, so this time we're going to go for a high pressure. Okay, and then we've got a negative, which means it's an exothermic reaction. So if we have an exothermic reaction, that means that we run it again at a low temperature to force it towards the exothermic side. Okay, right, hopefully you get those. There are some in your book which you can have a go at the end of your notes, which you can have a go. Just to look at one of the here, guys, maybe whenever I'm at it, about the change in volume, which I kind of spoke about earlier. So if we took just an example of that, let's go A plus B goes to C, gas plus D gas. Okay, we'll say delta H is positive, and we'll go 4 and 2. So again, the questions sometimes are worded a little bit differently. So they might say, for example, what happens to the amount of A and the amount of C if, let's say, we increase the temperature, and B if we decrease the volume of the container. So let's look first of all at the top one. So we have a endothermic reaction, which means that going in this direction I will take in heat, and going in this direction is exothermic. I will give out heat. So if I run this at a high temperature, I want the temperature to, or the heat to go down, so I want something that will take in heat. So therefore, what will happen to the amount of C? Well, the equilibrium based on this goes from the left hand side to the right hand side. Okay, and that means that the amount of A here is turning into C and D, so the amount of A will decrease and the amount of C will increase. Okay, so we're not just asked what happens to the amount of product or the amount of reactant, we've got to deal with both there. Right, if I reduce the volume of the container, so remember what I said right way back at the start of this lesson, reducing the volume of a container, and it's all gases in there. Okay, that is really what they're asking you there. What happens if I increase the pressure? That's all they're asking you. So don't be fooled by this sort of indirect question. So if I increase the pressure, again, I go back up and I count the moles on the left hand side, which is 6, and the moles on the right hand side, which is 3. And I remember back to what we said earlier, that if you increase the pressure, you move to the side of least moles. So that means that it will move from the left hand side to the right hand side. If I move into the right hand side, what's happened to the amount of A? Well, A is getting turned into product, so A, the amount of A will decrease, and the amount of C is moving from the left hand side to right hand side, so I'm making C, and so the amount of C would of course increase. So just to touch base on that little style of question that would pop up now and again and can on occasion throw people. Right, we're going to look at equilibrium with regards to industry. I've kind of touched on this already. The one that's on your spec is the Haber process, okay, which is the industrial manufacture of ammonia, and the conditions are, okay, Or the ideal conditions that we should run this at, okay, would be, let's deal with pressure first. So we're going from 4 to 2. So we're looking at a very, very high pressure. Okay, this is an exothermic reaction. Okay, so we're looking to run it at a low temperature. Okay, um, and if we actually look at it, it does run at a reasonably high pressure. It runs actually at a reasonably high temperature. So again, we have an iron catalyst in there. So why do we use these conditions if in actual fact these conditions will give us our best possible product? Well, if we look at the graph here, the temperature that this runs at is at about 450 degrees Celsius. The pressure that it runs at is about 200 atmospheres, which in actual fact, if we go across, excuse my wobbly hand, probably only gives us a percentage yield of about 27%. Now, if I'm taking my nitrogen and my hydrogen and I'm under these conditions, I'm only getting about 27% yield. So that seems really rather odd. Why would I not run it at a lower temperature? Okay, and why would I not run it at a much higher pressure? Because as we said earlier, those are the conditions that will give us the very best of the yield. Well, let's deal with low temperature first of all. Hopefully you can work out why would I not use a low temperature at this reaction. Well, that's to do with rate, because if I use a low temperature I get a low rate. So why not use a really, really high temperature to get a really high rate? Well, if I use a really high temperature, now I get a really low yield. And if you remember earlier, I spoke about the word compromise, and that's exactly what this is. I now get a compromise temperature use where I get a reasonable rate, a reasonable yield. Okay, let's look at pressure then. So we're using 200 atmospheres of pressure, whereas 400 would give us way, way higher. So why do I not use 400 atmospheres of pressure? Well, again, remember earlier, high pressure has got safety issues. High pressure is very expensive to maintain. Okay, high pressure has got very expensive factory setup costs. Okay, so but what's the good thing about high pressure? It has a really good rate. Everything's pushed in nice and close together, so we get a really high rate of reaction with high pressure. So we have all these negatives of high pressure, so why not then go the other way and use a really low pressure? Well, once you start using a really low pressure, okay, down here for example, you have a really, really poor yield. Okay, you also have a very low rate. So it's cheap, it's safe, the factory doesn't cost much to set up, okay, but your yield and your rate are so low that it's a complete waste of time. So again, what is our pressure? Our pressure is what we call, as we said earlier, a compromise pressure. Okay, so just in summary then, okay, a low temperature increases the yield of ammonia, but it's far too slow. A high temperature increases the rate, but the yield is too low. Okay, a high pressure increases the yield and the rate, but it costs too much money, both to maintain it and to set up the factory, and it's dangerous. And then our rate, because we are running at a lower temperature, we now have a catalyst, and even at that lower temperature, that catalyst will increase the rate. So that offsets our issue down here with using a lower temperature than we might use, even at this compromised temperature. With a catalyst in situ, we still get a decent rate. Okay guys, I realise that was a rather longer video actually than I had anticipated. I hope it covers all the bases with regard to your understanding of equilibrium, and you can do the questions at the end of your notes now. They are all, as I said, pretty similar to what I did and worked through with you there, so it's just a matter of you applying what we've learnt and working from there. Okay, all the best.